We will begin by introducing the idea of a factorial, and the factorial is part of some formulas that we'll discuss later in this video, the combination and permutation formulas. We describe n factorial, where n is a number, positive number. This expression has the implied meaning that whatever number n is, n read factorial, that's how we read the exclamation point, says you take that first number that you started with, n, and then you multiply down through the preceding integers. So if we started at n, then we next multiply by n minus 1. Then we next multiply by n minus 2, and we continue this pattern until we get to 2, and then finally until we get to 1. Now I wrote this in a generalized way with n factorial so that it would make sense with any number, but particularly as we're introducing a new idea, I think it could be helpful to see this with some actual values. So let's look first at 5 factorial. As I'm reading this, I would read the number 5, and then in this area of mathematics, if you see the exclamation symbol, we're not dealing with 5 anymore, but instead we're dealing with 5 factorial. And the implied meaning of 5 factorial is that I take the digit 5, which I started with, and then I multiply down through the preceding integers until I get to 1. So the preceding integer before 5 was 4, followed by multiplying by 3, then multiplying by 2, then multiplying by 1. And if you go through multiplying all the preceding integers, you will eventually end up at 1, and you always stop after you multiply by 1. So let's calculate exactly what is 5 factorial. It's 5 times 4 times 3 times 2 times 1. So 5 factorial, since it always follows this rule, will always be equal to 120. Next, let's take a moment and calculate 4 factorial. I'll give you a moment to write that on your paper. So at 4 factorial, 4 exclamation mark, we know we start at the integer 4, and then I multiply through the preceding integers. So then times 3, then times 2, finally times 1. Once I get to multiplying by 1, I know that I stop. Type that into the calculator, and we get that 4 factorial represents the number 24. Now take a moment to read this expression. We should see this as 5 factorial, which is some value. We actually just calculated that, it's 120. Then divided by 4 factorial, which we know is 24. So whenever we're dealing with calculations that involve factorial, you have 2 approaches. First, you could calculate them separately as we did here and here and then divide it. So 120 divided by 24. And we get the value 5. Another way that you could do it, if you don't want to calculate both, is write out what 5 factorial and 4 factorial is. So our other method could be to say 5 factorial is 5 times 4 times 3 times 2 times 1. I need to divide that by 4 factorial, but 4 factorial is 4 times 3 times 2 times 1. And an important mathematical rule to keep in mind is if we have a fraction that has the same thing in the top and the bottom, and there's just multiplication in between, then you can cancel common terms. So the 4 above cancels with the 4 below, the 3 above cancels with the 3 below, 2 above cancels with the 2 below, 1 above cancels with the 1 below, So the only thing left is this 5 term. And that's why 5 factorial divided by 4 factorial is just 5. So we've seen the example of how to deal with a factorial in general. So for instance, as just a quick review, write out what 8 factorial would be. Here we would start at 8 and multiply down through the preceding integers. And then if we type this into our calculator correctly, we'll get a value. We also saw how to do some calculations of different mathematical operations that happen to have factorials as part of it. Now, keeping in mind this last example, notice when we had 5 factorial divided by 4 factorial, when we wrote out the 5 factorial and we wrote out the 4 factorial, they shared all the same common terms except for the first digit 5. Let's expand this reasoning in this particular case to what I have written here, which is the general case, and I'm going to try to highlight why this pattern matches. It begins by saying in factorial. And then it divides by n minus 1. Notice the n minus 1 is in parentheses, and then we apply the factorial. So in our previous example, the n is the 5, and the 5 minus 1 is the 4. So we see this actually is a particular case of this formula. And in the particular case, the 5 factorial divided by 4 factorial just ended up being the 5. So with that in mind, could you predict in general if we ever have n factorial divided by n minus 1, then apply the factorial, what will that always simplify to? It'll simplify to n. And the reason is, if we write out n factorial, by definition that's n times n minus 1 times n minus 2, all the way down until we get to 2 times 1. Similarly, n minus 1 factorial starts at n minus 1. Now n minus 1 minus 1 is actually n minus 2. And then we continue multiplying through the preceding integers till we get to 2 until we get to 1. However, all of this taken together is exactly n minus 1 factorial, as is all of this. And whenever something's above in the fraction and below and there's only multiplication in between, those will cancel perfectly with each other, so that all we're left with is the n. So this is a helpful shortcut. So let's apply that in this case. 7 factorial divided by 6 factorial. This fits the pattern because I have an integer factorial, and then I'm dividing it by the preceding integer's factorial. We know by the formula this will simplify to just be 7. And if we weren't sure about using the formula, then just write out what 7 factorial is. Write out what 6 factorial is. And see that as we discussed before, these terms would cancel with each other. Let's continue to practice working with factorials. So we have 4 examples. In the first, we're asked to calculate 3, and then remember you read the exclamation mark as factorial. 3 factorial means take the value 3, and then multiply it by its preceding integers until you get to 1. 3 times 2 times 1 is 6. Now, before we do the next 2, focus on the difference in how example 2 is written and example 4 is written. Look carefully at the details. An important thing that we need to read in terms of the details shown on example 2 is notice that the 6 divided by 3 is in parentheses, and in mathematics you simplify what's inside parentheses first. This means I need to take 6 and divide it by 3 first before I ever apply the factorial symbol. So what's in parentheses comes first. Now 6 divided by 3 is 2. So this means I need to rewrite the inside of the parentheses as a 2 before I apply the factorial. Now 2 factorial means take 2, multiply it by the preceding integers. There's only 1, 2 times 1. So example 2 has value 2, whereas example 4 there is no parentheses, so I should instead read this as 6 factorial that is then divided by 3 factorial. Now I'd encourage you to attempt example 4 here, pause the video and work on this on your own, and then unpause to check your work. There's a few approaches here. Remember that we can write out what 6 factorial is, figure out what 3 factorial is, and then divide them. I personally prefer to just write it out and then cancel any common terms, and then that makes my calculation simpler. So I've written out what 6 factorial is, I've written out what 3 factorial is, and I cancel the commonly appearing terms, so that all I'm left with after cancellation is 6 times 5 times 4, which is 120. Now in our final example, it says take 6 factorial and then subtract 3 factorial. So in order to do this, I must calculate 6 factorial first, calculate 3 factorial. We already know 3 factorial 6. So let's off to the side calculate 6 factorial. And we get 720. Here might be a helpful hint. Notice when I write out 6 factorial, the past 5 terms is really 5 factorial. So it's 6 times 5 factorial. We know from a previous example 5 factorial was 120. So I could figure this out maybe a little more quickly if I knew 5 factorial was 120, because then it's just 6 times 5 factorial, and we'd get 720. So I have 720 minus 3 factorial is 6. 6 factorial became our 720. 3 factorial became 6. And then when we subtract those, we get 714. So this has just been some practice with finding basic factorials and then dealing with mathematical operations that include factorials. Let's now introduce the idea of permutations. We'll begin with this example. Suppose that Alan, Cassie, Maggie, Seth, and Roger are friends who would like to take a photograph with only 3 of the 5 possible friends in it. So of the friends listed, Alan, Cassie, Maggie, Seth, and Roger, not everybody will be in the photograph. They are curious that if only 3 individuals at a time were in the picture, how many different ways could they end up taking the picture? Now we can solve this just based on what we know so far. In a previous video, we learned about the fundamental counting principle, which said if you can break up a task into subsequent parts, then you can figure out how many ways each part could occur, and then the total way the process would occur is all of those pieces ways multiplied together. So the way I'm going to think about this is, imagine we had our 5 friends off to the side. So here's our 5 friends. They're waiting off to the side in order to decide how to stand in our photograph of only 3 friends. Now, does it make sense that if I have a photograph with Seth, Cassie, and Maggie, if I have Cassie first, farthest to the left, then Maggie in the middle, and Seth farthest to the right, that would be a different photograph than if instead Seth was farthest to the left, Maggie stayed in the middle, but now Cassie was farthest to the right. So an important thing to note in this example, even though it didn't come out and say order matters, we can think based on the situation that yes, the order that people stand up for a photograph is going to make a different picture, so it's implied that order matters. So going forward, if you deal with the problem, even if it doesn't specifically mention whether order matters or not, you need to think through the situation and think in that case, would order matter? And in here, it most definitely would, because changing the order of how they're standing up will make a visually different photograph. Now this is just 2 examples, 2 possible ways the friends could choose to stand up together. And I need to find all possible ways. So what happens is I have the 5 friends here, and each photograph is basically determined by who stands in the first position, who stands in the middle position, and then who stands in the third or the furthest right position. So I can think of this problem as overall a process with 3 separate pieces. I need to figure out who's going to stand at the farthest left, who will stand at the middle, and who will stand at the farthest right or the third position. Now, as we had all 5 friends here, we need to pick one of them to go here. Now, at this time, how many friends are available? 5. So we have 5 options of who will take the first place. Now, does it make sense once one of these 5 friends has stood here? Even though we don't know which friend took that place, we do know one of the 5 friends is now standing here. So there's realistically only 4 friends remaining who could now take the second place. Because of course a person couldn't stand here and then duplicate themselves and stand here. So we also realize we cannot repeat. So when trying to determine who could go to the middle position, we can't have the person who's already here, so there's now only 4 possibilities. And then by similar reasoning, the last position, 2 people have already stood up, so there's only 3 remaining people that we could choose from. So this is the number of ways each step could occur, so the number of ways the entire process could occur could be found by multiplying those. And we would get 60 as our possibility. There are 60 different ways we could create a photograph from the 5 friends if only 3 of the friends are in the photo. Now, so far this is a not new reasoning. We learned this kind of reasoning in our previous video. The reason we bring this up in our permutation section is that we could have also solved this problem through something called a permutation. And once we know how the permutation formula works, it's actually a nice shortcut. So let's see our permutation formula. So a permutation tells the number of possibilities for an arrangement from in total objects into a smaller collection of R objects, and one thing we need to note here is in a specific order. So for permutations, we need to say order matters and we can't repeat. That's the thing that you need to link. When can you use permutations? When order doesn't matter and you can't repeat the objects. So in this formula, n is the total number of objects you start with. And then just like in our last example, we started with 5 friends, but only 3 were in the photograph. We chose a smaller amount to be in the photograph. We start with n objects, and then we reduce that and only have a smaller number of R objects that we're arranging. So n is the bigger number, R is the smaller number. Once you've identified those 2 numbers, we write the expression mathematically as the permutation of n objects from n objects to R objects is equal to, and then we see this formula, n factorial, calculate that separately, divided by parentheses n minus R factorial. And remember, when parentheses are involved, we have to subtract first before we apply the factorial symbol. So this is an important formula. If you don't have these notes with you, then write this formula down on whatever scratch paper you have, because we will need to reference it in our future examples. Let's see why this idea of permutation will apply to our next example. Suppose we've been asked to judge an art contest that has 15 entries in all. How many ways could we assign first, second, and third place? Now, before we get started and focused on the formula, let's instead make sure we understand why in this situation order matters and we can't repeat the objects. The way we're going to think about this problem is, since we're asked to select first, second, and third place, the first artwork that we pick will be assigned first place. The second artwork that we pick will be assigned second place. The third artwork that we pick will be assigned third place. So the order that we pick it follows along with the order in the ranking. So order matters because if I had artwork A picked first, then artwork B, and then artwork C, the way we're thinking about this problem, that naturally means A gets first place, B gets second, C gets third. But if instead I had B picked first, then C, and then A, by how our labeling works, oh, I messed up the colors. No, I didn't. We'll go back to that. B, C, A. B would be applied first place because it was picked first. C would be applied second place. It was picked second. A would pick third place. Notice in both of these options, I've used the same three letters, A, B, C, but because order matters, if I picked A first, that's a situation where A would get first place. Whereas in this situation, A was picked last, so it got third place. So hopefully with this, we can see it doesn't just matter that we pick three objects, it matters the order in which we pick them because that will say which is assigned first, second, or third place. So that's why order matters here. Similarly, this example helps us see why repetitions are not allowed. If I had A, that would mean A as an artwork got first place, second place, and third place, which just isn't possible. Something needs to hold first place, something needs to hold second, something needs to hold third. The ranking makes it where you can't choose the same piece of art for all three awards. So that's an example why repetitions are not allowed. So we know why order matters, we know why repetitions are not allowed. Two key features that we need to focus on once we realize we can use permutation is what is the value in, and what is the value of R in this particular problem. Remember, n is the total number of objects that we start with, and then R is the number of smaller amount of objects that we're looking to arrange in a particular order. So read through our problem and think, what would you find n to be, and what would you find R to be? We started with 15 entries in all, so n is 15. We only want 3 entries ranked first, second, and third, so R is 3. And since order matters, our formula is the permutation of the total number of objects 15, selecting only 3 of those objects. We're going to write out the formula word by word and then we'll calculate it. It's the first number factorial, so 15 factorial, divided by parentheses 15 minus 3, close parentheses. We must write the parentheses here, they're essential, then factorial. Now, 15 minus 3 is another way of writing 12. So this becomes 15 factorial over 12 factorial. Now we're going to write this out completely by definition, and then hopefully as we do so, y'all will see a shortcut of how to calculate this more efficiently. Let's illustrate that. So we'll begin by just writing out the expression 15 factorial is 15 times 14 times 13 times 12 times 11, all the way down to the preceding integers till we get to 1. This is just the definition of factorial. And then 12 factorial is a similar pattern, except it starts at 12 and multiplies down through the preceding integers until we get to 1. And then what do we notice about this divided by this? It's the exact same thing, and we know in a fraction if you've got the exact same thing above, the exact same thing below, and it's only multiplication in between, then those will cancel, and this will become just 15 times 14 times 13, which is 2,730. Now this is no surprise that so many terms canceled, Because if you ever have a larger number factorial divided by a smaller number factorial, eventually they'll start repeating the exact same terms. Specifically, they'll always start repeating at the smaller numbers factorial, because 12 factorial would always have 12 multiplied by 11 all the way down to 1. And 15 factorial has that plus these extra terms at the front. So everything in common will cancel. So a way to think about a particular formula is if we have n factorial divided by n minus r factorial, it will always be the n times n minus 1 until you get to the term right before our n minus 1. So n minus r, I wrote that as n minus r plus 1. Now this is hard to see in symbols. We're much better just thinking about it in an example. So if I had 15 factorial divided by 12 factorial, I know that after cancellation, all that I'll be left with is the 15, the 14, and the 13. All values 12 and under will cancel because they'll appear at the top and the bottom. So if this shortcut makes sense to you, or if you think you've got it, pause and think about it a bit more, and you'll find it useful. It's a great way to simplify your calculations. If it doesn't make sense to you, that's okay too. You can always write out the factorials by definition and then see what cancels. Either way, you're going to get to the same answer if you've done it correctly. Our next example has 10 students are to be chosen from a class of 30 and then lined up for a photograph. How many such photographs can be taken? Now first ask yourself, in this example, does the order that the students line up for the photograph matter? If you had the same 10 students and you changed their order around, would it make a new photograph? And the answer to that is yes, order does matter, because even if I had the same 10 students, if they're in a different orientation, it makes a different photograph. We could visually tell them apart. Next, ask yourself, could I repeat the students? Could I have the same student standing in the first place and the second place and the third place? No, each individual could only stand in at most one place. So no repetition. Whenever I think about permutations, I always ask myself a few basic questions. First, order matters. That's important. Next, I can't repeat. The final question is, do I go from a bigger group to a smaller subgroup that I'm selecting? And in this case, yes, we started at 30 people. And then we want to winnow this down until there's only 10 people chosen. So we've gone from our bigger group to our smaller group. So because all of these criteria are met, we know we're dealing with the permutation. And we know our permutation formula is the permutation of the total n objects into a smaller collection of r objects is always n factorial divided by n minus r factorial. That's our formula from above. So all that's left is to identify what is n, what is r, and then correctly apply the formula and simplify your answer. N is always the larger starting number, so it's looking at the permutation of 30 people, selecting only 10 of them. And then take a moment to write out the formula if you know that n is 30, r is 10. I recommend you pause the video, write out the formula, and then unpause. So the formula says it should be the total number first, 30 factorial, over, now I do parentheses, 30 minus 10, close parentheses, must have the parentheses, factorial. Now 30 minus 10 is actually 20, so this is 30 factorial over 20 factorial. Now I could write out what 30 factorial is. I'm going to say it briefly. It would be 30 times 29 times 28 times 27 times 26 times 25 times 24 times all the way down until we get to finally times 2 times 1. 20 factorial would be 20 times 19 times 18 times 17 times 16, etc., all the way till we get to 2 times 1. As we're thinking about that, we notice once both the values start hitting 20 and below, those are going to cancel out. So this would simplify to just 30 times 29 times 28 times 27 times 26 times 25, I need more space, times 24 times 23 times 22 times 21. And then once they hit 20, they would start canceling above and below, and this is why we're only left with this. Now, I think this would be a very large number. Whenever the answer's extremely large like this, you do not have to calculate it further. You could have left your answer choice like here or here, or you could write it out like this, or you could multiply it all together and get the value. It's just for the extra large numbers, it's not particularly necessary. We just need to get to either of these answers. So far, we've introduced the idea of permutation. We've done a few examples involving permutations. Let's now look at the related topic of combinations. So the way you're going to differentiate between when you should use a permutation and when you should use a combination is that in permutations, order matters and we cannot repeat. In combinations, we similarly cannot repeat, but the difference is that combinations are when order does not matter. So if order doesn't matter, use combinations. If order does matter, use permutations. Now, the formula for combination is the combination of n objects, that's our largest number. Notice how it appears in the formula. Selecting down to a smaller group of r of those things, so r is a smaller number, is going to be equal to n factorial, all divided by the product of r factorial, so that's the smaller number, multiplied by in the denominator, parentheses, n minus r factorial. Now, just so we can see these compared side by side, this is the formula for permutation that we learned earlier. So the main difference between the permutation formula and the combination formula is the combination formula has this extra term in the denominator where we have the same term below, but then we multiply it by the new factor of r factorial. So keep in mind the difference. Permutations are when order matters, whereas combinations are when order does not matter. So let's think through in our next example why we would need to use the idea of combinations. It says consider all the possible subsets of size 2 from the larger set A, B, C, D. And then we're asked to list them. Now, sets were actually what we talked about in our previous chapter, so we want to keep in mind that in sets, remember, the order of the objects in the set did not matter. So if I have A and B, that's the exact same as B and then A. So notice the order that the element appears in the set doesn't matter, which is why it's a good candidate for combination. Also notice we started with 4 objects, which is the total number, and we want to select a smaller amount. So we had 4 objects, we want to select 2 of them, and order doesn't matter. So let's begin just by listing them all out, and then we'll actually calculate the total number using our combination formula, and we'll see that we get to the same number either approach. So I'm going to list out all the subsets in a systematic way, all the subsets that started with A, AB, AC, AD. Now I'll do all the subsets that start with B that I haven't already used. I've already used AB or BA because they're the same thing. So next is BC, followed by BD. Now we'll do all the subsets with C. I've already used AC, BC, so CD is left. And notice that's also the final subsets with D. So this is all the possible subsets of size 2 that came from the set A, B, C, D. Now in our checklist of thinking whether we should use permutation or combination, we first realize order doesn't matter. I naturally can't repeat because the set AA is actually size 1. We wanted subsets of size 2, so they have to have distinct elements. So order doesn't matter. We can't repeat. And we're going from a larger group, 4 objects, and we want to select a smaller group from those of only 2 objects. All of these idea, order not mattering, no repetitions, larger group to smaller group, mean we should use our combination formula, which we can see above on the screen. So it's the combination from the larger group of 4 objects to the smaller group of 2, and then take a moment to, based on our n being 4, r being 2, write out this portion of the formula on your paper. So that would be 4 factorial over, now r is 2, so that's 2 factorial, multiplied by 4 minus 2 in parentheses, then factorial. We know that we always simplify what is in parentheses first, and that would be 4 factorial over 2 factorial. Now 4 minus 2 is 2, so this is another 2 factorial. Now let's calculate those off to the side. 4 factorial is 4 times 3 times 2 times 1, that's 24. 2 factorial is 2 times 1, which is 2. So this will be 24 divided by 2 times 2, which is 24 divided by 4, and that would end up with 6, which is exactly what we saw when we listed it out. There was 1, 2, 3, 4, 5, 6 possibilities. So next I have an example of just some different types of problems we could see, and then I have them classified whether they should be a permutation or a combination. Keep in mind for combinations, if you see words like committees or group or team, those are indications you should use combination, because in a committee, group, or team, the order that you're in the team does not matter. It just matters that you're there. You're in the committee, you're in the group, you're in the team. There's no order implied. However, with permutation, it's going to be things like, for instance, picking first, second, and third place winners. The order that it's picked indicates a different place, which means it's different. As we've seen before, arranging people for photographs because the order that they're in the photograph matters. If instead of just picking a team, we were picking members on the team, so picking a captain, picking a pitcher, picking a shortstop, that would be a permutation type problem because the order that they're picked gives them a different position on the team. So if there's ever an idea that the order that I pick something gives it a different meaning, that's going to be a permutation. Whereas if all that matters is that I pick them to be there, but the order that I pick them does not matter, that would be a combination. So these are some options. Take a moment if you'd like to pause the video and read through it, but these are examples of when a permutation should be applied, when a combination. The basic idea is order doesn't matter for combinations. Whereas in a permutation, order definitely matters. Now it just happens that many of our examples will discuss cards because it's an easy reference, there's different descriptions, it just works very nicely for counting problems. However, I know not everybody might have played a card game, so if you're not familiar with cards, then this table will be helpful for you. First of all, it shows that we have 4 suits. These are our club suits, diamonds, hearts, and spades. So for a normal type of card deck, we have 4 suits. They're all listed here. Notice I've got 2 suits that are black colored, clubs and spades. 2 suits that are red colored, diamonds and hearts. And this is important because sometimes a problem will say from the red cards, sometimes from the black cards. Now each suit has 13 cards. So let's count the number of clubs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So every suit has the same 13 cards, just with a different symbol attached to them. And in particular, every suit has 3 face cards. The face cards are the jack, king, and queen of each suit. So if there's 3 face cards in each of the 4 suits, how many total face cards are there? 3, 6, 9, 12. So keep in mind there's 12 total face cards. How many total cards are there in all? Well, each of the suits has 13 cards, so there's 13, 26, 20, or 13 more is 39, plus 13 more is 52. So there's 52 cards in all, split into 4 suits. Every suit has 13 cards, and then every suit has 3 face cards, the Jack, King, and Queen of that suit. So mark this page in your notes. You might find it helpful later on to flip back to it as we deal with problems that say so many cards of this suit, so many face cards, etc. We have an example involving cards coming up next. It tells us that a common card game is poker, and in poker, 5 cards are dealt to each player from a standard deck. So whenever we say a standard deck, we're just saying there's nothing wrong with it. It's the 4 suits. Each suit has the 13 expected cards. And we know the standard deck in all has 52 cards of all together. Now, whenever we talk about a hand of cards, that's just a phrase in terms of cards. That's going to be when you're dealt, you have card 1, card 2, card 3, card 4, and card 5. So imagine you already have these 5 cards in your hand. Would it matter if you as an individual, if they're already in your hand, move this last card and switch places with the first card? It wouldn't matter. You would have the same 5 cards in your hand, just in a different arranged order. So to visualize this, imagine this was one of the hands that I got dealt: a 10 of diamonds, 5 of hearts, ace of hearts, 8 of hearts, 4 of hearts. This is what I'm holding in my hand right now. And if I move this 4 of hearts in front of the 10 of diamonds, it does not change the fact that my cards are still 4 of hearts, 10 of diamonds, 5 of hearts, ace of hearts, 8 of hearts. So in a hand of cards, once they're in your hand, the order no longer matters. Now, just so we can visualize this, let me deal again. And this is my new hand of cards. So I see I have a 8 of hearts, 9 of hearts, king of clubs, 2 of clubs, 5 of clubs. Again, once these 5 cards are in my hand, if I switch their order internally in my hand, changing the order does not change the 5 cards that I still hold. So to answer this question, if the cards are already in your hand, does the order matter? No. Order does not matter, because I still have the same 5 cards. And since order does not matter, that makes me think of combination formula when dealing with cards, because the order doesn't matter. So next we're asked, how many different 5 cards hands are possible? Well, the idea is if we're going to use combinations, we have to know what is the starting total number of cards I could draw from. And then from that larger number, I want to select only 5 of them. So the smaller number is definitely 5. So R is 5. Think about what was the total number of cards that I could have drawn from. That would be 52. Because at the beginning, I could have chosen from any of the cards in the deck. There was 52 options to select from. I'm only selecting 5, and order doesn't matter, so that means I use the combination formula. The combination from 52 objects down to just 5. We know the formula, if we look at our previous formula, it was n factorial over r factorial times n minus r factorial, where n is 52, so this is 52 factorial over r factorial, which is 5 factorial, times 52 minus 5, close parentheses, then apply the factorial. I'll need to simplify this. 52 minus 5 is 47, so this becomes 52 factorial over 5 factorial times 47 factorial. Now, since both of these are very large number factorial, that's a good thing because much of what occurs at the top will then eventually cancel with what's at the bottom. Because remember, what is factorial? 52 factorial would be 52 times 51 times 50 times 49 times 48 times 47 times 46, all the way down to times 2 times 1. I definitely do not want to write all of that out because I'm going to end up canceling most of it, because right below is 47 factorial, which means 47 times 46 times 45 all the way down to 2 times 1. The only thing that won't cancel between these two is the starting term of 52 from the top, 51, 50, 49, 48, because once we get to 47, it will cancel perfectly with what's below. Now, 5 factorial, we need to rewrite this. So at the top we have 52 times 51 times 50 times 49 times 48. That's what did not cancel. The bottom canceled perfectly. The 47 factorial canceled with the 47 factorial at the top. And then we're left with 5 factorial below. Now, with practice, you're going to associate 5 factorial as 120. So if you know that, you could have just written divided by 120 below. And I think this will be small enough that we can calculate this out. So I have 52 times 51 times 50 times 49 times 48. So I'll write that carefully. Divided by 5 times 4 times 3 times 2 times 1, I know is 120. I'll divide those. And we get 2,598,960. So if I'm dealing from a 52 card deck and I'm dealing 5 cards, there's 2,598,960 different ways I could deal a 5 card hand from those 52 cards. Now, if you think you're getting the hang of when to use permutations, when to use combinations, when to use fundamental counting principle, I'd encourage you to do these next 3 examples on your own. Pause the video, attempt them on your own, and then unpause to check your work. If you'd still like to see these ideas kind of guided through, then just watch the video without pausing, and we'll work through them right now. So in our first example, it says, how many 4-digit numbers are there? And let's just read through the next examples too, so we can get an idea of their differences, and then we'll come back to this. In the next example, it says, how many ways can 3 of 8 people line up at a ticket counter? So there's 8 people in all, but we only want 3 of them to line up. And then the final one is, how many ways can a committee of 3 be selected from a group of 12? Now, one thing I hope we notice in both of the last 2 examples is, notice we started with more people, 8 people in this group, 12 people in this group, and we wanted to get to a smaller collection in the first example to 3, in the second example also 3. So both of these had the idea of a bigger group selecting down to a smaller group, except they differed in that the second example, if people are lining up, does the phrase line up, does it imply that order matters or doesn't matter? I would say order matters when we're lining up, because the person who lines up first would get help first versus the person who lines up second and the person who lines up third. They're not just collecting together in a group. There's a meaning to their order. So here I would say order matters. Whereas in this next one, if we're just selecting a committee, we know all that matters is that we're on the committee. There's no implied order about this person was picked first for the committee, so they have some meaning. No, it's just if you're in the committee, you're in the committee. So here we would say order does not matter. So both of these examples have the idea of bigger group to smaller group, which generally bigger to smaller means either permutation or combination. And then the way you choose between permutation and combination is you ask yourself, does order matter or not? Because if I'm going from bigger group to smaller group, which I am in this second and third example, but if order matters, then I have to use permutations. However, if I'm going from bigger group to smaller group as I am in the third example, but order does not matter, then I use combinations. And our first example is in a completely different category because notice it's not saying select from this bigger group a smaller subsection. It's just saying how many 4-digit numbers are there. This is our fundamental counting principle because in the fundamental counting principle, if you're making a 4-digit number, you have to pick the first place to the left, which is the thousands place. Then you have to pick the hundreds place, then the tens place, and then the ones place. So it's the idea of picking a 4-digit number is picking 4 places, figure out how to do each of those separately, and then multiply it together gives you the entire way to do the whole process. And this particular example was the topic of our previous video, whereas example 2 and 3 are what we're talking about in this video, permutations and combinations. So that's an overview of the different strategies we use for each of these. Let's focus now on the first example. Remember when it says how many 4-digit numbers, unless they specify otherwise, the digits that we're allowed to use are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, since we're not otherwise restricted. Now, I'd like you to consider, could I put any of these digits in the first digit to the left, the thousands place? Consider, could any of those 10 digits go here? Consider if I wrote down this possibility. Does this meet my criteria of being a 4-digit number? I have 4 numbers written, but it's not really a 4-digit number. This is a 3-digit number in disguise, right? 0, 1, 2, 3 is 123. So if you're asked a 4-digit number, remember that 0 cannot come first. Because if 0 comes first, you're not really writing a 4-digit number, you're writing a 3-digit number in disguise. So in terms of how many options could go in the first place, you could use 1, 2, 3, 4, 5, 6, 7, 8, 9. You could use 9 possibilities, but we could not have 0. Now here they did not say repetition wasn't allowed, so it's implied that it's okay because I could 33333 is definitely a 4-digit number. So now that we've dealt with the first decimal place, which we had to avoid 0, there's no reason why I couldn't have 0 in the subsequent locations because it's no longer an issue of being 4 digits or not. So for the second decimal place, I could use 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So there's 10 possibilities. And then since I can repeat, there's 10 possibilities for the third place and 10 possibilities for the second place. So that would be 9 times 10 times 10 times 10, or 9,000 possible 4-digit numbers. So we've previously discussed why we would use permutation for this next example, combinations for the last ones. I'm going to write down the permutation and combination formula. So once you know you're using permutations, always copy down the formula so it's visible. Similarly, I know in the last one I'll use combination, so I'll write down the combination formula. If I write this down in general, I'll probably be much more consistent in finding the correct answer. So I have the general formula. Now in particular for our second example, I started with 8 objects. I wanted to arrange 3 of them when order mattered. So I had 8, that's my total number. I'm selecting 3. So to follow my formula, it would be 8 factorial over 8 minus 3 factorial. Now, I think we've done enough examples that you might have noticed, oh, 8 minus 3 is just 5, so this is going to be 5 factorial. You could have definitely in your head subtracted 8 minus 3 and then just written 5 factorial. Feel free to do that, or you could write it out and then in a next step simplify it. Now 8 factorial divided by 5 factorial, I could write out 8 factorial as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I could write out 5 factorial as 5 times 4 times 3 times 2 times 1. And then I could realize, oh, they both have 5 times 4 times 3 times 2 times 1 as part of it. Those terms would cancel and I would only be left with 8 times 7 times 6 because all later terms were in above and below, so they'd cancel. Now 8 times 7 times 6 is 336. So there's 336 different ways for 3 of the 8 people to line up at a ticket counter. Next, our final example, because it's a committee and order doesn't matter in committees, we're going from a larger group to a smaller group. We know we use the combination formula. Here in particular, it's the combination from 12 as the larger group to only 3. And our formula says you take the factorial over 3 factorial times 12 minus 3 factorial. Now this would be 12 factorial over 3 factorial times 9 factorial. Now I'm just going to write all of these out just to help people visualize. If you're comfortable saying, oh, with the 12 factorial over the 9 factorial, all that would left after you cancel is 12 times 11 times 10, keep going with your work. I'm going to write that out so we can see. 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And then 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We see that we have the same items above and below. The 9 factorial appears as a portion to each. Anything that's the same above and below, and there's only multiplication, will cancel perfectly to where we're only left with the 12 times 11 times 10 at the top over the 3 times 2 times 1 that didn't get canceled. Now this is going to simplify nicely. Let's calculate the top. 12 times 11 times 10. That's 1320. 3 times 2 times 1 is 6. Divide that by 6. And we get our answer of 220. Is what the whole calculation simplifies to. So there's 220 ways that we could take from 12 individuals and select 3 of them when order does not matter. So a good way to assess your progress with what we've learned in this video and the previous video is, are you comfortable with why we did the fundamental counting principle in this example, why we use permutations here, and why we use combinations here? Because each problem is slightly different and it was necessary to use a different approach in order to solve it. In the first example, if we can ever break up a process into separate pieces, then you can find out the number of ways you would deal with each piece, multiply it all together, and that's the way you would deal with the total. If instead we're going from a bigger group to a smaller group and order matters, we use the permutation formula. Contrasted with if we're going from a bigger group to a smaller group but order does not matter, then we use the combination formula. Let's continue working with these formulas. It says, how many ways are there to choose from a team of 7 from a class of 20 students in order to make a basketball team? Now, one thing I first notice is we've got the idea that we're choosing from a larger group. We have 20 students to start with, and then we want to select to a smaller group of only 7. So this is the idea of bigger to smaller. I know that that fits in a certain pattern. If I've got a bigger group to a smaller group, I then need to ask myself, does order matter or not? Because if order doesn't matter, it's combination. If order does matter, it's permutation. So think of the way this is phrased. We're choosing people for a team. Does the order matter when we're choosing a team, or does it just matter that the 7 people are on a team regardless of the order that they're picked? In terms of a team, order does not matter. So will we use combination or permutation? Since order does not matter, we are going to use our combination formula. If I need to, I reference back in my notes and I write down the general formula. The combination from n total objects into r smaller is n factorial over r factorial times n minus r factorial. Now for our particular example, n is 20. We started with the larger collection of 20 students. We're selecting only 7, so that's 20 factorial over 7 factorial times 20 minus 7 factorial. The bottom would simplify. 20 minus 7 is 13. And then here we simplify. I know that top is 20 factorial is going to be 20 times 19 times 18, etc., all the way down to 2 times 1. And it has most in common with the 13 factorial. There will be a lot of cancellations here. In fact, these two will cancel together until all that we're left with at the top was 20 times 19 times 18 times 17 times 16 times 15 times 14. 13 and below is shared, so they cancel. The bottom was 7 times 6 times 5 times 4 times 3 times 2 times 1. This term, the 13 factorial, canceled with the 13 factorial that was part of the 20. If we'd like, we could just type the top into our calculator, divide it by the bottom. However, if you'd like to simplify further, 7 goes into 14 2 times. 5 goes into 20 4 times. Let's see what else we could do. 6 goes into 18 3 times. Now this is not necessary. You could have just typed it in as it is. This might make my calculations a bit easier though. 16 and 4 goes into 16 4 times. And then finally I think I could get 3 goes into 15 5 times. So this will give me a smaller number where I have 4 times 19 times 3 times 17 times 4 times 5 times 2. Everything at the bottom canceled except 2 times 1. So that's going to be 155,040 divided by 2. So if we start with 20 students and we only want to select 7 and order doesn't matter, there would actually be 77,520 ways to complete that. Next, we're asked how many poker hands consist of 5 red cards only. Now, we introduced a little bit about cards and the idea that a poker hand has 5 cards. So whenever we read poker hands, we need to remember that there's 5 cards in a poker hand, and it was dealt from a standard 52 card deck. So we started with 52 cards, we dealt only 5, and then remember, once it's in your hand, order does not matter. So with that in mind, bigger idea to smaller, we're dealing with combinations, but actually I need to specify a little bit more. In the 52 cards, there's all 4 suits, right? If you look back at our previous diagram, you'd see spades, diamonds, hearts, and then clubs. But this problem specifically says we only want red cards. So in actuality, we did not want to be dealt with from the clubs or the spades. So since it says red cards only, we did not start with 52 options because that means we could have got one of the spades or one of the clubs in our hand. We only wanted red cards. In fact, we were only dealing with the 2 red card suits. There's 13 cards in each suit. So we had the 13 diamonds and the 13 hearts. So together we were dealing with 26 possible cards as our total because we were okay with anything from the diamonds, anything from the hearts. From those 26, we're only choosing 5. So we know our general combination formula. We always write that down off to the side. 1, it's helpful just to have this visually close by for reference. 2, the more times you write it, the easier it will be to remember the formula. So for our particular example, we were starting with 26 cards because we're only using red cards. That's why we're using 26 instead of 52. We're selecting only 5. The formula tells me it should be 26 factorial over 5 factorial times 26 minus 5, then factorial. Now this can simplify. Okay, 26 minus 5 is 21 factorial. And the 26 factorial and the 21, a lot's going to cancel there. Because remember, what is 26 factorial? It's 26 times 25 times 24 times 23 times 22 times 21 times 20 times 19, etc. down to times 2 times 1. 21 factorial starts at 21 times 20 times 19 times 18 all the way down to 2 times 1. So whenever you cancel what would occur from the 26 factorial and the 21 factorial, all that you'd be left with is from the bigger one, you had the 26 that didn't cancel, the 25, the 24, need a bit more space, the 23, the 22, and then once you got to 21, it started canceling with what was at the bottom. So we've dealt with this, divided by, I guess they didn't cancel perfectly. I want to watch that notation. The 21 got canceled with what was at the top. That's why we didn't have anything from 21 below there. But we still had the 5 factorial, which is 5 times 4 times 3 times 2 times 1. We also know that 5 factorial is 120. You could replace this with 120. Let's calculate the top. You could also do some cancellation if you want, like I did in the previous example. You could say 5 goes into 25 5 times, 4 goes into 24 6 times, etc. But if that's too complicated, just calculate what the top is and divide that by what the bottom is. Here you want to make sure you don't make an error typing something in incorrectly for sure. Five times 4 times 3 times 2 times 1 is 120. And we get there's 65,780 possible ways to get a 5-card hand from only the red suits. Now our next example is a bit more complicated because it's actually going to apply the ideas that we've learned in this video of combinations, along with the idea of our last video, which is saying if you can break a process into multiple steps, calculate the number of ways each step occurs, and then multiply that all together for the total way the entire process will occur. So here in this particular example, we want to be dealt a poker hand, but particularly we want to have only 2 kings and 3 queens. Now the only way to ensure from the cards that were dealt that we would get these options is I'm not actually drawing from all 52 cards. Of course you would actually be doing that, but remember, if we're calculating the number of ways this could occur, we need to calculate how many ways in total could this occur. So we're saying I do not want to get anything that's not 2 kings and 3 queens. So it's a bit different because we're restricting what we could possibly draw from in order to ensure that we get these particular outcomes. Now we know in terms of the kings, there's a king of hearts, a king of diamonds, a king of spades, and a king of clubs. And similarly, there's a queen of each of these as well. And the idea is in our hand, we only want, of these 4 kings, we only want 2 of them. And then of these 4 queens, we only want 3 of them. So in order to construct our hands, we might pick our kings first, 2 kings first. That's the first part of the process, followed by the distinct, because picking kings is different than picking queens. Pick 2 queens. Next. So what I want us to see here is that in order to pick a 2 king hand and a 3 queen hand, we have 2 distinct portions of our process. We first need to pick the 2 kings, then separately we need to pick the 2 queens. Excuse me, I should have written 3 queens here. So we pick the 3 queens next. And then remember, if you can break an entire process into pieces, once you know the number of ways the first piece occurs, the number of ways the second piece occurs, then by what we learned in our last video, we would just multiply those together, and that's the total number of ways the entire process could occur. So this is kind of our meta structure of the problem. Now we still need to figure out how to pick 2 kings and how to pick 3 queens. Once we know that, we multiply it together and we're done. So in terms of picking the kings, these are all the options that you could draw from because these are the only possible kings. There are 4 possible options you could pick from. How many of those do you want? You want 2 kings, so you're picking from 4 2. And then once it's in your hand, order doesn't matter. So this is the combination of 4 things, selecting only 2. Now similarly, when we're thinking about picking the 3 queens, remember if you're picking a queen, it has to be one of these 4. Now from these 4, how many queens did you want? 3. And remember, once it's in your hand, order doesn't matter. So this is combination, going from 4 things to 3 things, and order doesn't matter. So write in how would we express in symbols as we did in the picking 2 kings. What's the formula for picking 3 queens? The combination from 4 things to 3 things. Now, both of these are numerical values. I just have to calculate it off to the side. Once I know what they are, I'll multiply them together and we'll get the overall answer. So I'm going to write the formula for each below. The combination of 4, choose 2. 4 factorial over 2 factorial times 2 factorial. Multiplied by, now combination of 4, choose 3. 4 factorial over 3 factorial. Now 4 minus 3 is 1, so that's times 1 factorial. We'll calculate each of these. Now 2 factorial is 2 times 1. 2 times 2 is actually 4, so I'm kind of simplifying this as we go. 3 factorial is 3 times 2 times 1. 1 factorial is 1 times itself. So we have 3 times 2 times 1. That's times 1. That's actually 6. So this first one, and this will give us 4 times 3 times 2 times 1 is 12 over 4 times, excuse me, it's not 12, it's 24. 4 times 3 times 2 times 1 is 24. So 24 over 4 times 24 over 6. Now this will simplify to give us 24 divided by 4 is 6, times 24 divided by 6 is 4. So there's 24 possible hands that would have exactly 2 kings and exactly 3 queens. So in this particular process, it actually combined the fundamental counting principle and the combination formula, because in general, we could break up the entire process into 2 distinct parts. That's the fundamental counting principle. That's why I had my 2 blanks. And then the number of ways each portion could occur, calculated, and then multiplied together. And then in terms of picking 2 kings from 4, we had 4 things. We only wanted 2 of them, and order doesn't matter. That's why we use the combination formula. In terms of picking the queens, we had 4 queens. We only wanted 3. Order doesn't matter. That's why we use this combination formula. Now, our last topic of this video I think is very nice because it's very visually distinct problems. This particular formula will only be used in terms of arranging things like letters, pretty much, in our class. So anytime you're asked to determine the number of ways you could arrange the letters in this word, you need to think of this formula. Now, what is this formula in particular? There's a lot of symbols. Let's zoom in and talk about it, and then we'll apply it to the examples below. Suppose I have some beginning set of in objects. And while I explain it in this problem, since this is such a symbol-heavy formula, I'm going to reference the corresponding idea in the main example. So for our example, the number of objects in is how many letters we see written. So 1, 2, 3, 4, 5, 6, 7. In here equals 7. Now, in the set of in objects, in this example, some of the objects are going to be repeated and some are not repeated. Now, for the letters of Florida, no letter is repeated more than once. But if there was a letter repeated more than once, so maybe Florida's not the best example since it doesn't have everything, let me write in another one. So instead of Florida, because it doesn't have common letters, let's use the word college as our example. So in the word college, I count the number of letters that are given. 1, 2, 3, 4, 5, 6, 7. So in is 7. But one thing that I hope we notice is that the letter L is repeated twice, and the letter E is repeated twice. So in sub 1 is the repeated object of that type. So for us, we're saying the letter L is repeated twice. So in sub 1 is 1, because that's kind of representing our L. And then what's representing E is the next one, the next repeated digit in sub 2. The subscripts are just the first repeated, the second repeated. And here, I misspoke. It's not that in sub 1 is 1. The L is repeated twice. So in sub 1 is 2, because the L appears twice. The E also appears twice. So in sub 2 is 2. Now, no other letter is repeated. C is by itself, O is by itself, G is by itself. So in this particular example, we would only have up to in sub 1, in sub 2. But you could have as many repeated objects as possible. You would just list it out. Then the number of ways we could rearrange these letters, although not all arrangements would make actual words, but you could imagine the total number of ways we could arrange these 7 different letters, even though the letter L is repeated twice and the letter E is repeated twice, is given by this formula. So for us, it would be 7 factorial over 2 factorial times 2 factorial. So the way I want y'all to think about this is the top number is just the total number of letters given, counting repeats, factorial. And then you divide out by repeated letters how many times they appear factorial. So for us, the 2 factorial here represents the fact that I had L twice. The next 2 factorial represents the fact that I had E twice. And then I can simplify the top and the bottom, and that's the total number of ways that we could rearrange the in objects where some of the objects are repetitions. So let's look at our next example. For the words Florida, I first count how many letters are given. 1, 2, 3, 4, 5, 6, 7. So in is 7. I next ask myself, does anything repeat? So are there any letters that are used more than once? In this particular example, there is no letter that's used more than once. So there's no in sub 1, no in sub 2, no in sub k. So it's just going to be 7 factorial. I don't have to divide out by anything because there's no repetitions. Next, let's look at the example of rearranging the letters that comprise Google. So remember, you first count the total number of letters, 1, 2, 3, 4, 5, 6. Total number of letters is 6. Next, you ask yourself, does anything repeat? I see G repeats itself twice. O repeats itself twice. So the total number of letters is 6. The first letters that are represented is my G's, and they occur twice. Next, I have the O's. They also occur twice. The L and the E don't repeat. So the formula tells me it's the total number of letters, factorial, divided by the repeats by how many times they occur. So G occurs twice, so that's 2 factorial. times 2 factorial. Now let's actually calculate this. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1 times 2 times 1. So the top is 720 divided by 2 times 1 times 2 times 1 is 4. So there's 180 ways that we could rearrange the letters of Google. Now our final example of this type is how do I rearrange the letters involved in the word apple? And I'd encourage you at this point to pause the video and attempt it on your own, and then when you're ready, unpause to check your work. So here we count, there's 1, 2, 3, 4, 5 letters in total, so N is 5. Next I look for repeats. I see P occurs twice. None of the other letters occur again, so my N sub 1 is 2 because there's 2 P's. The formula then says it's the total number of letters, factorial, divided by any repeats, factorial. There's only one group of repeats, my P's. So this is 5 factorial over 2 factorial. We know 5 factorial is 120, 2 factorial is 2. So this is 120 divided by 2. So there's 60 ways that I could rearrange the letters of apple in distinguishable ways. So just reviewing what we learned in this video, we introduced the idea of factorial. We learned how to work with formulas that involve factorial symbols. We then said if I'm choosing from a total number of n objects, a smaller collection of r of them, then if order matters, I use the permutation formula. If order does not matter, I use the combination formula. And then next up, these last types of examples were if I was rearranging the letters in a particular word, it's always the total number of letters present in the word factorial, and then you divide out by any repetitions of letters. You calculate how many times does the repetition occur, and it's that number factorial for all the repetitions, and that's always on the bottom of the fraction. So keep in mind this formula. Here are our repeated letters, where N sub 1 is the number of times the first letter is repeated, number of times the second repeated letter is repeated, etc. So remember, as always, if you have questions, just reach out to me and I'll be happy to answer your questions.